close that, send this over to the same Windows OBS, which is going to be 4. Oh, I guess I already had something there. So I'm going to swing this back over. Wouldn't be one of my streams if it wasn't kind of janky, I guess. Maybe I should work on that. Have better production quality and whatnot. It's probably something to do. All right. I was just, I don't think anyone's here yet, but this guy, Code Opinion, oh my god, is this guy cracked. He knows, like, so much. It's unreal. It's kind of tough to, like, so there's a phenomenon where, like, when someone is better than you at something, some people just, like, they can't see that. And so it's, like, hard to know exactly when someone is a lot better than you at something. But, like, this guy, he knows a lot about programming. Like, a lot. This is a real 10x engineer. And, yeah, it's interesting. It's interesting. Yeah. What's up, Johnny? How's it going? So I have a bunch of problems on the midterm list to work through for a real analysis. Man, math has been really hard, but, like, I don't know. I went to the library today for the first time in a while, because I've been studying at home mostly, and I was just, like, overhearing people's conversations, and it made me feel better about myself. Like, not to belittle anyone else, but I don't know. I was just hearing people, like, not, like, working that hard and, like, on their phones and whatnot, and, like, coming there for the socialization, and I was like, yeah, it does require, like, a lot of time to grind hard STEM subjects. Like, it's easy to, like, if you're surrounding yourself with similar STEM people, to be like, man, like, how is everyone so damn motivated? But then, like, you're surrounded by people that, like, aren't, like, grad school bound, and you're like, oh, I'm kind of in the minority here, actually. I don't know, that's just my experience. And, yeah, I feel quite shaky about a lot of analysis proofs still, but, like, I don't know, I was realizing, like, I've covered it. I've got a good amount more comprehension than I was expecting. It just, like, sneaks up on you, subtly. I'm doing real analysis, number theory, evolutionary robotics, and then this linguistics class. Okay. What am I showing? I also got... People put me onto this PDF reader, Sioyek. Or Sioek. I don't know. But this thing, like, makes me... I recorded a video about it. This thing is so good. This is, like, software wet dream. It's... Oh, my God. I just love this thing. Like, that is awesome. I need to figure out, like, multi-page mode, and I also rebind a couple of things. But that's cool. Confirm that's really assuring when you're the one in the trenches and then you hear someone with the basic question from the first week of class. Yeah. Yeah, good to know we have experiences. Okay, this is good, Alexander. Which problems are easy and which ones are hard? I was thinking also, like, it would be good to make this practice, like, more deliberate, even though it would be, like, more painful for me, I'm assuming. Like, I really want to be, like, forced to think about these problems as much as possible and, like, build my understanding as much as possible. And, like, having feedback about more granular details of proofs and stuff would be pretty cool. And yeah, I guess I should go over which problems are easy and which problems are harder for me. So all right, this is just from the problem sheet. So I would say like convergence and finding the limits of stuff, like a problem like this, I wouldn't find terribly difficult. We know the limit's going to be 2, and then I know pretty well like the epsilon limit definition now, and like how to set that all up and what the quantifiers mean, and like the proof structure overall. What I get stuck on still, unfortunately, is like the algebra, where sometimes like certain inequality things, like I don't know, I don't have the intuition fully there for solving those reliably, I would say. Like I know most of the major tricks now, like difference of zeros terms, the triangle inequality, like Bernoulli's inequality, and recognizing like advanced factoring problems. But with that being said, there's just a lot of times where like there's some kind of reduction in the size of the inequality that I intuitively like am not thinking of myself. Like once they're explained to me, I get them, but yeah, I'm not coming up with them myself reliably. So like in the context of passing this exam, like I feel honestly fairly good already. I could do like 90% of the shell of this proof and be like, okay, there's 2 steps of algebra from getting this to this, and honestly, like this is total cop out, but I suspect, based on people playing Instagram or watching Instagram reels in my class and stuff, this teacher is going to be somewhat lenient on grading, and just because math is quite hard and like they don't want people to drop out of a state school because of tuition, like it's not going to be insanely hard to pass this test just by like I can get away with doing that, if that makes sense. Like if I mess up some of the algebra, it's not like the most rigorous, serious entrance to a grad program or something like that. It's like I will survive the class no matter what. But just for my own, like building my own mental architecture, I would like to understand the proof structures like more rigorously and have that intuition. And I'm an undergrad, yeah. I think, yeah, just for myself, that would be nice. And let's see, what other questions are there? Show that xn is strictly increasing, xn is bounded above by 3. Conclude that xn converges. So this one, I'm not entirely sure. I guess strictly increasing. Yeah. This is interesting because it's almost like a series, but like a multiplication series. If you're looking at the exponent as, yeah, I don't know. That one, like the strictly increasing, I guess the definition is just like x of n is less than x of n plus 1, and then you just plug it in and verify that algebraically. And then xn is bounded above by 3. Seems like you could maybe do a trick where you substitute in, I don't know, you treat this as like an expansion with Bernoulli's inequality, maybe? If you, or not Bernoulli's inequality, with the binomial theorem. And yeah, that is E. And if you expand that all the way out, maybe you can then transform it. I want to try that, actually. That seems like a solid exercise. Problem 2. It's simple, but it cuts right to the fundamentals that I want to drill. So how do I do this? I guess, do I have an exam review yet? Okay. I don't really need a preview for it. I'm just bringing this next to. Oops. Where's my terminal? window managers get pretty confusing sometimes. I'm just storing things in funky spaces. See a recursive sequence lurking? And recursive sequence usually involves like the Cauchy definition, right? Okay, so this is defined as 1 plus 1 to the n. And so we could say let, well, okay, so for part A, using algebra, to show that x to the n is less than x to the n plus 1. How would I do that? I mean, okay, so on one side, we would have 1 plus 1 over n to the n. On the other side, we'd have 1 plus 1 over n plus 1 to the n plus 1. Okay. And I'm going to actually open a new preview of this. All right, how would that be done? I mean, so I could bring one copy down. And would that help exactly? Not really. I don't see it canceling out. This might be like a Bernoulli inequality question. So you could split that up into yeah. So I'm wondering, like, maybe. Okay, well, I know I'm gonna try Bernoulli's inequality. It's just taking me a second to like come up with what that actually is gonna be churned out. So 1 plus 1 over n. I guess I'll write out the whole expansion and just try to derive Bernoulli's inequality. It'll help me memorize it. So it'd be 1 plus, well, it's like the binomial theorem is going to be a b to the 0, and we don't have to worry about the choosing stuff because they're ones. And then we're going to get plus like a squared b to the 1 plus dot 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 plus a to the, well, a is going to just go to 1, or eventually 0. And then this is going to be b to the n minus 1. And then we can use Bernoulli's inequality with this and take like, oh, actually, violently suppressing my urge to give hints. It is a pretty rough estimate. I mean, also, like, it's tough because I'm taking away elements on that side of the inequality. It would be nicer if I was taking away elements on the other side of the inequality, I guess. Like, if I used Bernoulli's on that side. Yeah. But yeah, that's, I'm not seeing that very clearly exactly either. I mean, I wonder if like looking at it like this will be any different. And getting rid of the exponent, well, it would still be to the n. Oh, there could be some just basic algebra here with like increasing the power of oh, yeah, this is interesting. So like I could safely get rid of this 1 because it's on that side of the inequality. And increasing it will make this side bigger. And then, I mean, that seems pretty self-evident to me, because this whole thing is greater than 1. So we're increasing over that. That seems like it would hold up. Although, wait, no. I'm actually not sure that's fully allowed, because you might be on the wrong side here to do that. But on this side, we could do that maybe. Which, yeah, I mean, is the same as getting rid of this. Take the nth root. Well, that's... not allowed to use the derivative yet. That's a bit too optimistic. All right, I mean, okay. That felt intuitively right to me, but I could be wrong for sure. I mean, if we're increasing the denominator of this term, this overall term is getting smaller, which means this overall term is getting smaller, and we're on this side of the inequality. So, I mean, and it's like just, it's the equivalent thing with a higher exponent. That seems valid to me. If that's invalid, speak up. Fortunately, 1 plus 1 over n plus 1 to the n is already smaller than 1 plus 1 over n to the n. So this estimate is already too coarse. is already smaller. Oh. Yeah. Yeah, I see. I see this estimate is too coarse. That's not like really, that's not what we're trying to prove exactly. That doesn't work out. Because that's like, I, I was working from the desired result backwards, but like illegally. So like, if you're doing this in reverse, you can't just do that. Like we can't increase. We can't get rid of the n or the plus 1 here. So that doesn't work that way. Just expand both sides and convert the terms of the RHS to multiples of 1s on the RHS. Oh, so what you're suggesting is expand this with Bernoulli's inequality, or not Bernoulli's, the binomial distribution. So if you have on this side 1 plus 1 over n, you get 1 plus, why is my syntax highlighting messed up? What is this? 1 plus 1 over n times 1 plus 1 over n squared plus dot 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 plus 1 over n to the n minus 1. Or is it to the n? I always forget with those things. I mean, if I do it inconsistently on both, the algebra should still work out. Yeah, whatever. Using j multiple times. Okay. And then we're going to get is less than this, except all the terms are going to be to the plus 1. And we're going to go up to n of them. I guess it's kind of confusing to like yeah, I this is making slightly more sense to me now too. Like what people say about working backwards, like what I was doing with those inequalities is very wrong, but like if you're you have to go from things where like the algebra is bidirectionally true. There is a way to do this elegantly. You have to recognize that the abstraction to algebraically comparing these expressions is repeated, alternating between addition and multiplication. Recognize the obstruction to algebraically comparing these expressions is repeated, alternation between addition and multiplication. Are you talking now at this step where we've got way to recognize this elegantly? You have to recognize that the obstruction to algebraically comparing these expressions yeah, binomial coefficients. Yeah, I'm a little like my ability to regurgitate correctly the binomial sequence needs to be absolutely drilled in. Like what the coefficients are. It's like n choose n choose, okay, n choose, and then it goes up to n. The n is always at the start, so I mean, yeah, it's like, I guess it's symmetric in these, so maybe it doesn't hugely matter, but do we have choose? Binom, maybe like that. N and 0. Let's see. Yeah. Thanks. And choose 1. Binom n and 2. Oh, that should be around this. Binom n minus 2. Oh my god, this is fucked up. No. That was before the ... Okay, what am I doing here? Okay, yeah, we have each of these terms. That would be n choose 3. What's the comma doing in there? Or n choose 2, sorry. Oh my god. Binom, and I think by typing this out, it'll help me remember it more. And then on this side, binom n0, binom n1, binom n2, binom n, or n plus 1 n. I mean the original ones. Where the coefficients should both go one step further. Okay, one step higher on both sides. Yeah, man, I'm getting absolutely whipped into shape here. But it's sick. So the exponents go all the way up to... Did they go all the way up to... Yeah, n choose n. I don't know why I thought they stopped early. This would be n plus 1, choose n plus 1. And then this would go all the way up to, oops, n plus 1. Okay, all right. So that's the binomial distribution. And okay, the original ones, Alex said, there's a way to do this elegantly. You have to recognize the obstruction to algebraically comparing these expressions as repeated, alternating between addition and multiplication. Oh, okay, I want to look, repeated addition between, repeated alternation between addition and multiplication. Yeah. Yeah. You're comparing like n of these with n plus 1 of these, but this itself is like less than this. And so, yeah, you have to recognize this obstruction to algebraically comparing these expressions is repeated, alternating between addition and multiplication. And yeah, that's crazy. So inside here, like, you're kind of comparing against this one, but it's like there's many of these being multiplied. I want to go back to that in a sec, but I think I kind of get what you're trying to say. Notice how the multiplicity of the cumulative powers remains equivalent to the exponent of the main expansion. This will help you avoid losing any terms. Thanks, yeah, that's good. So, shit. So each one of these terms is less than its equivalent term, I guess. But there is an extra here. We have up to n plus 1. So we could we like pair them off in a way that we're like scooching this one over a little bit to compare it? I mean, I'm not recognizing this immediately. Like factoring. Or. Yeah. Think about the order of both sides. Oh, okay. Well, this term, as we go along, it's getting less and less and less. But the binomial will like make kind of a curve, but it's like going downward overall. And same thing here, but it's like just starting a little ahead. That's how I understand it geometrically, but yeah, Pascal's triangle is really good for remembering the coefficients. Yeah. But in this case, with like I know it's roughly in like a pyramid shape, and this is decreasing, but shows up literally. Wait. Okay, n to n plus 1. Wait, n arrow n plus 1 or n greater than n plus 1. Oh, n to n plus 1 implies 1 over n plus 1. Goes to 1 over 1 plus n plus 1. Oh, wait. What? N? Wait, I get what you're saying, though. Which makes me think, like, I'm doing way too much work with this binomial distribution and comparing things. Like, let me write this out from my memory of what you just said and this is maybe just the way better way to prove it. If n is going to n plus 1, we want to show that n is less than n plus 1 implies this is like very obviously increasing, and we want to show that we can derive our sequence from it. And So we can add, we can do that to both sides very safely. Divide by n because n is positive, I'm assuming. Well, maybe it's positive. I'll worry about that case in a second, but and then just add 1 to both sides. Oops. Oh, what? And then just exponentiate both sides. And then we've gone from like a known increasing sequence to is an addition-like computation step and is a multiplication-like computation step. Oh, are you meaning this for like use of within analyzing the binomial distribution? Addition-like computation step. And that's a multiplication-like computation step. N goes to n plus 1. Rewritten now is quite sketchy. That is quite sketchy. I feel like wait, just for my learning experience, what's specifically sketchy about it? Is it this last step? Because I feel like leading up to doing this, like everything is fine, but like once you do this, that's a little bit weird. Because this might not necessarily be, like adding another one of these into the multiplication might be bad. You can compute the coefficient, it will make it easier. I might even dare to say that 1 over n is less than 1 over n plus 1. Trying to motivate my reflexive compulsive desire to 1 plus 1 over n as n plus 1 over n. Yeah. Okay, cool. N n plus 1 over n. I mean, yeah, writing it like that does make it a bit easier to compare, arguably. The highlighting is so messed up on this. Okay, all right. And then I mean, oh. Oh, Big Pepe's here. Because doing so moves all the addition steps to the back and the multiplication steps to the front, and makes the expressions algebraically compatible. Yeah, that's really clever. Jeez. So wait, right here, by doing that expansion and then transforming, oh wait, I guess I made a mistake in doing this. But we're showing that compound interest monotonically strictly increases. One approach others recommended is to use the binomial theorem expansions. Oh, he's just like giving that to Pepe. Compute the coefficients. Okay. Nth root test? I'm not sure. Yeah. Okay, and what I have written now is not the same as what was written before. 1 plus it's not. Oh, yeah, I'm missing the 1. Jeez. 1 plus 1 over n. Avoid using the binomial expansion. Okay, I'm game with that. At least I got to write it out. I mean, I think so. If you have 1 plus 1 over x to the n, and but it helps to narrow down other methods which are more or less significant. Yeah, I don't think we could differentiate. We haven't really covered the derivative in class. So try to motivate 1 plus 1 over n as n plus 1 over n. n plus 1 over n, and on this side, I mean, could rewrite that to I want to see I would try reading n plus 1 choose k over n plus 1 to the k as a function of n choose k. Oh, right, on the left-hand side. You mean like that? Wait, no. Sorry, I feel like I'm just dialed in on this. This should be n, and now I don't need this to the n, or I need an extra per n. There we go. Jesus. Took me a minute to come up with the right-hand side. Oh, n plus 1, n plus 1. Yeah, as good as you are at math, you don't know left from right. Wait, I want to see your logic for because doing so moves all the addition steps to the back and the multiplication steps to the front. This makes the expressions algebraically compatible. What do you mean to the back? Were you talking about it in context of the binomial expansion? Probably. I'm trying to motivate my... n plus 1, whatever n plus 1, 1 plus, whatever n plus 1, 1 plus. Yeah, that message is hella confusing. But yeah, I'm sick. AMGM? Each expression is computed as a function of n. I'm visualizing the AST of the expression. Whoa, this guy is wicked smart. That's crazy. Visualizing the AST of the expression. The abstract syntax tree. QM, QM, GM, HM. What is AMGM? Arithmetic, geometric. Arithmetic, geometric. Oh my god. Wait, are you serious? Is that real? Do you mean using that to get rid of the exponents? The arithmetic mean of n elements is greater than or equivalent to the geometric mean. Geometric mean. No, it's the same one. AMGM. So you can use that for more than two things, so maybe n plus 1 in our case. N plus 1. Oh my god. Oh my god. So you're saying by AMGM, we do something like, this is outrageous. This inequality wizardry is crazy. So you do something like that. This is a greater than or equal to. Oops. Where does that get us, though? We have to do the same for the other side. So I'd rearrange it. What do you mean rearrange it firstly? Whoa, wait a minute. Navy. I haven't really taken proper mathematical ML now. There's a guy in my Discord though that's like gonna run a seminar on it eventually, so I might live stream like watching that. Multiplying the consequence. If you multiply the consequence, alright, I'll check out your blog post. You mean of n plus 1 squared? Yeah, try to prove e is increasing. N plus 1 over n. 1 plus 1 over n to the n equals n plus 1 over n to the n. Yep. Equals n plus 1 to the n over n to the n. Oh. You're saying, man, my like ability to pick out these algebra tricks is like rusty. For sure. Second line, you have a strange. From the first line, move the factors of n plus 1 to the same side. Yeah, just email me. I'll let you in. The second line, you have a strange. From the first line, move the factors of n plus 1 to the same side. Oh, I guess you guys are somewhat saying the same thing. This parentheses extraneous. So like throwing a well, oh wait, we're multiplying by, we would have n plus 1 squared is less than n plus 2 times n to the n. Missed the right-hand side exponents. Missed the right-hand side exponents. You mean the n? Where did that go? Oh, what am I fucking doing? What is this? This should be... This algebra is freakily wrong. What's up, Mr. Creature? Yeah, the second line is wrong. I'm redoing the second line. So the strategy is taking n plus 2, n plus 1 out of this. And it's now just to the n. No, wait. That is weird. Better would be to move this around. Like just to represent this as each of these terms. Man, my algebra is pretty bad overall, but practice is how you improve it. So each of these terms is going to be e to the n. And then it's actually going to be to the n plus 1. Oh my god. Okay, and then swinging that around. Could we get this would be n plus 1 and now we're going to end up with this on the other side, and this piece will get put there, but it'll be multiplication. And then we're adding n, so we'll get 2n plus 1. The AMGM trick will work. It just kind of comes out of nowhere. I don't like this problem anymore. Algebraic and geometric multiplicities, bro, from linear algebra. The AMGM trick comes out of nowhere. Yeah, because this, I don't know, this algebra, like, what am I doing anymore? Oh, fuck. That's what it was. Damn, I blanked on that. Yeah. This shit right here is wrong. The way to do this is with that geometric multiplicity. I completely forgot about that. So that's less, yeah. And then we are taking away, geometric multiplicity takes away the exponent of this whole thing, and then allows us to divide by n plus 1. Damn. No, that's my bad. That's my bad. I was just forgetting that. So like that. No, it was right. This is overcomplicated now. AMGM inequality was something new to me, I guess. The version you have of AMGM is only for two things. You want x1 up to xk over k is less than root k. AMGM clipped. Sounds crazy that it's the intended solution. Still not clear to do what a set of numbers you could, to what set of numbers you should apply it. inequality this over n yeah, what? There's probably a different solution. I mean, what about the solution of taking the nth root of both sides? Although that doesn't seem right to me. Not immediately obvious to what set you should apply it. Yeah, it's not. Yeah. Yeah, nth root doesn't look promising. I agree. Okay. So here, like proving that I just don't see how this algebra immediately works out. Clear the denominators from the second line. Third line looks bad. Clear the denominators from the second line. You mean get something? I mean, this is what I did before, kind of, but like this would be moved over. Like, I feel like this is what I had before. Rose ignoring ATP. What's ATP? Yeah. This is what you had before I was right. Okay, I second guessed myself. But, okay, so the invocation of the AMGM is here now. Think of a GM between n and n plus 2. Revisit the definition of AMGM. So dividing by n. Oh my god, yeah, and you need the multiplication in there too. So this is greater than each of those terms. And we've got this to the n plus 1. Would we get something like... it's this summation. It's the summation of a bunch of n plus 2s over n plus 1. Stop and think about what you're looking at. Should be able to see now why the inequality happens and why it's subtle. That's comparing n and n plus 1 at the very beginning isn't good. You should write the given sequence into a sum and then compare it with the next n plus 1 term. This is just unnecessary. Comparing n and n plus 1. Should rewrite the given sequence. No, I'm still not sure exactly why the inequality happens. And you're talking about the AMGM inequality? You can now try AMGM to add an n plus line on the next line and create a coordination. Oh no, there's beef. Create a correlation to the former line. Try AMGM to add an n plus 2 on the next line and create a correlation to the former line. What's with all the racial profiling? Yes, try and improvise the inequality you saw to the n and n plus 2. Do you want some? Go back to topology, I wish. Some British guy trying to fly. Okay. Try to improvise the inequality you saw to the n and to the n plus 2. The problem-solving philosophy, that's interesting. The problem-solving philosophy. Wait, Alexander, you're seem like a wicked smart guy in some ways. Like, what you imagine with the abstract syntax tree is like, it's kind of crazy. Do you like visually see math most of the time? Like, how do you think about these things as like visual structures? His team made some significant. Okay. We're multiplying a bunch of n plus 2s together. Look for the ideas. There are some people who only see fluency with using techniques as important. That's like really fascinating to me because hold on. What do you mean how many? I just wonder, like, how did you develop the mental models that you have? Like, do you think about a lot of the world like that? Because I was thinking about this, asking or like, um, talking with a friend about this too, who like, um, who was like running in some insane math circles. Like his roommate was the top mathematician in China who solved like an air dish problem, and he said, yeah, there's some kids that the way they think about math is like it's either visual or it's just like different than the way people normally think of math. And like visual, I'm not talking about geometry, I mean like visualizing or at least like intuiting mental models for like more complex structures. And for some people that can do that proficiently and look at the ideas as things that fit together, like it's much easier for them to just kind of look at an area of math and get an idea of what it's like. um, I don't know what I am exactly saying, but whenever you get a solution that you couldn't find yourself, you try and think about how you would have found it yourself. That's interesting. Yeah. There's value in being fluent in these techniques that builds intuition, and you can also explore more things faster. Just look for the ideas. There are some people who only see fluency with using techniques as important. Yes, how many? Can't explain myself well over this. Yeah. I mean, if you want to hop on a call sometime, I'd love to hear your explanation. Not very deep insight on these types of problems. Yeah. Okay. How many? I mean, over n plus 1. Are we going to have like a summation in the final form here? Like, can we take this? Oops. And turn it into like this? We probably shouldn't have n. Going from like k equals 1 I employ it once in a while, like 10 minutes on math. Knavy. So I like algebra where the rabbit hole goes very deep and straightforward statements can often be interpreted in an insightful way. Cool. This is a very common pattern where if you fix a plus b, a times b reaches maxima when a equals b. Area of a rectangle. Wow. Yeah. Jeez. When a plus b, a times b reaches maxima when a equals b. That's so clever. Yeah, I'll hop on a call, Johnny, if you're around. Yeah, honestly, like, progress on math homework is like, it's wicked hard, dude. It's like slow. But I don't know. Talking to like a classmate today, I was like, okay, I can kind of feel the difference in my comprehension. I know things a little bit more. Well, I don't know. At least I thought I did. Yeah, it goes in and out. So here, a equals n, b equals n plus 2. Extremum is at a equals b, n plus 1. You're doing the most. Oh, sweet. Just call me when you want. Otherwise... Okay. Well, I'm wearing headphones, I don't think. I think it'll be fine. Hello?
What's up?
Hey, Johnny. How's it going?
How are you doing?
Pretty good. Pretty good. You know.
Nice.
Can everyone
You
hear
managed to
you?
get over,
Did I manage to what?
the sickness?
No, I'm still kind of sick, honestly.
Okay.
I'm hoping if I like do enough math, I can increase my brain's temperature enough to eradicate it.
Yeah, that's always a good idea, right? Smoke it out.
Spin the engines a bit. Okay.
Okay, so for this first one, right? I have one of like these AMGM solutions,
Yeah.
but it's like I said, it kind of comes out of like thin air. Like it's not that nice. And although I have to say, like what the other people were saying, like about these, like some things just straight up look very wrong about like taking the nth root and stuff.
Yeah.
But like you probably can't do it with the binomial theorem. But it will not be very pretty either. Like so I think this will be fine in the end.
Yeah. You think this is the path of least resistance? Although Big Pepe says he's a solution without AMGM.
Yeah, probably with his shit ton of algebra. Also, by the way, I think what Alexander was trying to convey to you with like the how many thing was you have this inequality, and you know that you're multiplying 2n plus 1 things on each side, and it's kind of like you expect it to kind of balance each other out, right? On the left, I have n plus 1, and I do 2n plus 1 times itself, while on the right, I have, in total, I also have 2n plus 1 things, but n of those are just n, and then n plus 1 of them are n plus 2. So you expect it to like tip the scales ever so slightly in the favor of like the right side, because you have more n plus 2s or something. I think this was the kind of thing.
Oh, yeah, I see. Yeah.
Yeah.
I guess I wasn't
So
looking
it doesn't like tell you really what, like, how much or how to prove this, but it kind of gives you an idea, I think, why it might be true.
Yeah. And that's because we have this n. I don't see how the algebra exactly works out in combining the right-hand side into 2n plus 1, though.
I mean, it doesn't directly. It's just you have n of the n terms, like, and you have n plus 1 of the n plus 2 terms.
Oh,
So
yeah,
I
see. I see.
Plus 1 term. Like, there's nothing more deep, at least that's what I think.
Yeah, I see what you're saying. And that does give a little more insight, but how would you actually prove with like AMGM that you've got more n plus 2s?
Exactly. Like, how does it actually? So for AMGM, we're gonna use like what you have kind of in the second line, right? So for AMGM, we want to cook up some set of real numbers to which we can apply this inequality. So what if you go back to, like, I don't know if you still have like the wiki open or something, if you go back to the inequality so you can see what we actually can choose.
Yeah. Yeah. I mean,
so yeah, first of all, in our mind, I think we want to, if we have that inequality, to raise both sides to the nth power, so there's no nth root in there. That already makes it a bit clean, I think.
Okay. Yeah.
And the inequality is still, right, like raising to the nth power. These are all positive numbers. Like, this doesn't change anything about the inequality.
Sure.
So let's think in our mind. So we need to make some choice of x1 through. Well, they also use n again as a variable, but n has a specific meaning for us. So let's think about x1 through xk. We have to make some choice of x1 through xk, and also, make some choice of k.
Yeah.
And then see what pops out of this inequality. So what I did, which is not nice at all, is I'm gonna choose as our k, I'm gonna choose n plus 1. So we want to cook up n plus 1 different numbers. And what I'm gonna do is, for n of those, I'm gonna choose n plus 1 over n, and for the last number, I will choose just to equal to 1. And then I'm gonna say that's gonna work out. Yeah.
Okay.
Which
n plus 1 over n.
I can share my screen a little bit.
Sure. Yeah.
Because I wrote it down on my tablet anyway, so you can see what I mean. Otherwise, like, doing this to
n plus 1 over n. Yeah.
Screen.
All right.
Do you see it?
Yes, I do.
Okay, so on the top here, let's have fun color. This is what we have. Like, for a choice of x1 through xk, this is the inequality we get. So what I'm gonna choose is, or like the equivalent of that is down here. So through my x, so our let me write it down here. Our k is gonna be n plus 1, and then x1 through all the way through xn, so all but 1, I'm gonna choose to be n plus 1 over n, and then the very last one, so xn plus 1, I'm gonna choose to be 1. So these are our like 3 choices that we get, and now we just plug these into the inequality, and we see what happens. So let's start with the right hand in pink. This should correspond to this down here. So if we multiply all these things together, I get n copies of n plus 1 over n. Just multiply with each other, and then I multiply by 1. Well, that doesn't do anything, so we see that indeed the 2 pink things, they correspond to each other. Like these are the same thing underlined in pink. And now we consider the well, let's just choose the other fun color. Let's do yellow. Like these 2 things underlined in yellow correspond to each other. As in, I'm literally just plugging it in. But the bottom thing in yellow, we can now simplify slightly. As in, I have n terms of n plus 1 over n. So those just add up to n plus 1. And then I have one more plus 1 in the, what's it called in English? Numerator or denominator?
Oh, like yeah, I see how that works out,
And then and then we divide by n plus 1. And we have raised this whole thing to the n plus 1, because that's what we chose for our k.
Wow, yeah.
So, and then we get that thing on the left.
Dude, that's insane. Yeah. That is amazing.
Yeah, it's fun. But like this is like supposed to be an exam question, right? This is absolutely fucking diabolical. Ask this on an exam, I think.
Damn, that is, that's crazy. And it's interesting. Like, I guess the way I've been thinking about these problems is like a little bit backwards. Like, you're kind of starting from this inequality and like deriving the end result. I feel like I keep starting from the desired result.
Yeah, I mean, that's in general, it's like a very valid strategy, right? Especially in analysis. I mean, I can show you, like I did work under here. I did some sketch work where I also immediately, I just start with the end result and see what I need. And I got a lot of the same things that you did. But like it didn't work out. Where, I just try to reduce some algebra and see like what would imply what and what would I need, and make some guesses, and then they turned out to be wrong. So for now, this is also my my only solution.
Yeah. Wow, that is I would not have thought to like guess those 2 partition points. And
it's not straightforward at all.
Wait, you're bound by the constraint that all the x terms like equal each other, but you're free to pick whatever n you want.
What exactly do you mean?
Just in the inequality, the AMGM inequality. Oh yeah, okay, I see. So you're picking all the terms separate from this n.
I think there's like some constraints that they have to be positive. Non-negative real numbers, whatever.
Yeah.
And I guess to be like really specific, the equality, like because it's like a non-strict inequality, and they mentioned the equality holds if and only if like all the numbers are the same.
Yeah.
Which is not the case, right, for us, because n plus 1 over n will not be equal to 1. So one of them will be different. So the inequality here will actually be strict for us.
Yeah.
So this is actually what we need because we want the sequence to be strictly increasing. So I guess that's one more detail.
Yeah, that makes sense. Yeah. Huh. Okay, sweet. I guess someone pointed this out in the comments and or in the stream, and I slightly suspect this too. Like, based on the other people in my class, like, I don't think that this is gonna be an exam question. Like, we didn't
Yeah,
exactly cover. I honestly, my professor like sometimes like has to look up like an algebra trick. I don't know if she would know to do that off the top of her head in class.
yeah, this is not nice. Like, I mean, on the other hand, analysis classes, like, I don't know, like at least for me, they were always like infamously hard tests. Like, I think for mine, like after the retake, the first year, like what 45% passed the class, something diabolical like that. But this was also like some new teacher giving it for the first time. This was some crazy shit. It was also peak COVID lecture, just reading off a PowerPoint presentation.
Yeah, brutal. Yeah. Um, yeah.
Yeah, yeah. I hope that like something like this is not an exam.
And
Although
Pema
Italian
says,
Italian professors can be kind of crazy. Not gonna lie.
yeah, she said like in Italy they cover all analysis like before calculus, or they don't cover calculus in their math curriculum, really.
Yeah,
They
yeah.
cover,
True. I think I heard in Germany they kind of do the same thing where it's like your first semester you just start doing analysis and you never actually get a calculus class, right? Like in high school you do calculus and stuff, and then you just do calculus properly, quote unquote properly, like the first time, where you immediately start learning everything with its proof and just do analysis,
yeah.
which is not how I did it. I mean, it can be done. I don't know if it's the most useful thing to do. I think it's very depressing. I would have hated it for sure, doing so much analysis.
Right. Yeah.
But yeah, some people do crazy stuff.
Yeah. I think okay, and then she's also asking for like boundedness, and I mean like clearly this is bounded by E. But
Yeah, but that's yeah, but I think you're going down a circular argument there, right? Because we like the next step after you've shown boundedness is to conclude that it actually converges and that number you call E. So it
yeah.
sounds like
Right. Yeah, I
uh,
see. I see. Yeah.
yeah, you can't. That would be a nice trick, but it doesn't work. Because what does it say in the question? Like bounded by
Bounded by
3 or
3.
something.
Um,
Let's see. I've not thought about this.
the algebra might be like I remember in the book the trick for doing this sometimes is like clumping an expansion and then kind of upper bounding certain parts of it.
Yeah. That's always a good trick. Just let's see. I've just literally I've not thought about it. Uh, whatsoever. Mm.
Yeah, bounded by 3.
I think like for this, it might be useful to do something like what was it? Binomial theorem.
Yeah. Oh,
I don't know. Seems like it might be.
Yeah, I guess this was the technique I was talking about.
Let's see. Yeah. Which I think, yeah, that's especially useful when you have like a series, so like a sum of terms.
Yeah.
You can like just like keep estimating those terms.
Right.
But like if we use the binomial theorem, we can kind of turn this into a series. Kind of
Yeah.
not
True.
really, but in spirit.
Yeah.
Spirit at least.
Which would be 1 plus n choose 1 times 1 over n plus binom n2 times 1 over n squared plus a bunch of terms plus binomial of n 1 over n to the n.
Let's see. Yeah, exactly.
That's a little bit, that notation's a little bit cursed, but
Well, I get what you mean. Kind
yeah.
of cursed that those brackets the one though, but yeah.
Oh yeah. Okay, and so like, could we group this in a way that things get
Yeah, I mean, in the end,
canceled?
we just want. Okay, they want the bound by 3, but it will probably fine. We need to if we can like, yeah, we want to somehow get rid of those coefficients, right? Those binomial coefficients. Because then we would be quite happy.
Yeah, it's tough. I mean,
like, what does this binomial divided by that even look like? So you have this n factorial, and then you have some. What is it? I factorial divided by n minus I factorial. And that's 1 over n to the power I.
that's, why did you think to do that? Like, look under the hood at the definition of binomial.
Like, normally I would like to really avoid that, but here it's like I don't have anything else to go on, so that's what we like. I'm out of ideas, so I have to go back to actually writing out the algebra. That's like what it comes to.
Yeah, I see. Yeah.
We would be very happy just with an upper bound for each of those terms.
True. And the binomial, like, the binomial terms just make it tricky because it's kind of hard to estimate. I mean,
yeah, they can be like rather large.
right. They
Yeah,
do
so
get
like
large.
what can we even expect? Let's think about this way. N over I, binomial terms. Like, if we think about the nth row in Pascal's triangle, this will get pretty big, I think.
Yeah,
Right?
yeah, they can get quite big.
I'm literally just gonna look up Pascal triangle. Am I embarrassed as an algebraist to look this up? No. Let's see. Yeah, they go pretty hard. Like, they go pretty, yeah. Those are some big ass numbers in there. which in general, like they're going to be much bigger than n. Like they might also be bigger than our n to the power I. So we can't expect some like really small number to come out.
Yeah, that makes it pretty tough because I mean without it it's very simple to say each of those whatever n terms is like bounded by, I mean they're all less than 1. You could group them somehow, but
yeah. What if we, another nice trick is, what if we just see how quickly they grow by taking the quotient of successive ones? Like, what if we give this thing a name, right? Let's call Ti is like this nth term, or that ith term in this sum. And like, what if we just do like, because we kind of, what if we do like Ti plus 1 over Ti? Because like these, I'm doing their quotients because in their definition, it's like a lot of multiplying going on. So I think like things will cancel out quite nicely actually if we do this. So my Ti is like n choose I times 1 over n to the power I.
Your Ti is plus 1 over what?
N choose I times 1 over n to the power I. So we have like a sum of n terms.
Oh, I see.
Dependent on I.
Yeah.
And each element I call Ti. So.
Right.
So let's see if this even helps. So if we do Ti plus 1 over Ti, like we have a lot of, it's like very written multiplicatively. So I hope like things will cancel out. So for example, if we just look at the powers of n, we will be left with a 1 over n. And then we will have this binomial coefficient. We will have n over I plus 1 divided by n choose I. I guess I should say choose and not over.
Yeah, so you're saying like once the algebra all cancels out, or once the n terms, you would get like something like this.
Let me just write out the definition. 1 over n. We have like n factorial over I guess the n factorials cancel each other out. Which will be really nice. What you write is true, you're just forgetting a 1 over n in this portion. Right? Because we have a 1 over n to the power I plus 1, and we divide it by 1 over n to the power I.
Right. Oops, that's within the binomial. Yeah. And the factorials all cancel out?
Well, I'm writing it out now. I don't think they will all cancel out, but there will be a lot will cancel out, which is quite nice.
Oh my god, yeah. There's a lot of factorial algebra to... Expanding this is
Well,
n minus, it's n minus the bottom, n minus I minus 1 factorial.
oh yeah, I think something nice will actually come out. Yeah, because let's see. I think if we can get some constant bounds, that would be very nice.
Whew. That's...
Yeah, so right, we have like a lot of factorials, but note that the n factorial,
yeah.
those who cancel out against each other.
The n factorial.
And then we have like an I factorial versus and we divide that out by I plus 1 factorial. So we will just be left with I plus 1 in the bottom. And then with the n minus thing, it will also cancel out nicely. So we'll get like only an n minus I at the top.
Yeah. I see. Yeah, there's just a couple manipulations you have to do of the factorials that's slightly tripping me up. I guess the I plus 1. Wait, so on the bottom, are we going to get an I plus 1? And then here,
Yeah,
we're going to get a n minus I minus 1.
At the top, you should get an n minus I. So in the end, it will be like 1 over n, that we just had from before, and then n over I, n minus I divided by I plus 1.
N minus I. Like this? Oh.
Yeah, your cam is kind of covering it up, so it's hard to see.
Oh. This n minus I minus 1. No.
Yeah, but you don't get an n minus I in the bottom, I think, only at the top.
So you're just left with n minus I over I plus 1.
Exactly, and then times 1 over n.
Okay. But what does that tell us? That's just the rate of...
Wait, you also don't get the n minus I minus 1 at the bottom. It all just goes away. It's just, yeah, like just simple like that. So you get n minus I over I plus 1 times 1 over n. well, this is already a lot simpler. And now I want to give an upper bound for this much more simple thing by removing the dependence on n. I would like to get rid of that n. I think then we're in very good business.
Okay.
So can I, maybe you can cook up a way to give an upper bound for this so that we remove the dependence.
We remove the dependence of n.
In the meantime, I'm just buying myself some time to think, like, how I want to continue this.
Wait, I guess I'm confused on. We're finding the ratio at which this binomial distribution kind of thing is, well, yeah, it is increasing, but this is like, what is showing something about the ratio give us in terms of boundedness?
Maybe not immediately, but if we have a upper bound for this, because so this will give us how much bigger is the I plus 1 in terms of the I. So my plan is to then leverage this and do that all in terms of like give a bound, like how much is the case one in terms of the first one, in terms of just some constant.
Oh,
so
that is interesting. Yeah.
In terms of T1 or T0 or something along those lines.
Yeah. Wow. Yeah. And what's the logic with not wanting this in terms of n again?
That will help us to do it, because we have an exact expression for our thing. It's just the dependence on the n makes it really annoying to give an upper bound. Like, if I can make it only in terms of I, and I can estimate each ti just in terms of I, then hopefully I'll be in good business.
Yeah.
That will make it hopefully a lot easier, and then hopefully it's I'm gonna make it like an easy expression in terms of I, which I'm very, very hopeful now that this will work out nicely actually.
Gotcha. Yeah. Is the method to getting rid of n here just algebraic?
Yeah. Now it's just shuffling a little bit to find an upper bound. It doesn't have to be like the craziest, tightest upper bound ever. Just there will be a quite natural one. So that also gives me hope that we're on the right track, because it goes quite naturally.
Yeah. Yeah, I don't know. My ability to be creative with this algebra is just completely dried right now.
Yeah, fair enough. Don't worry. It's not immediately obvious. So what if we just switch out those two things in the denominator? So we consider it like it doesn't change anything, but what if we think about it as n minus I over n, and that's times 1 over I plus 1.
You mean split the partial fractions?
No, nothing so complicated. It's really nothing deep going on.
And then on the bottom, and I plus n. What did you? No, sorry. I'm trying to see exactly how this would make sense.
Well, you don't have to multiply out the bottom. You just think of it as like two fractions. You think of the one fraction, which is n minus I over n, and then you multiply it by some other fraction, 1 over I plus 1. And like one of those fractions, only one of those fractions now contains n and can easily be bounded.
I see, yeah. Yeah, why didn't I think of that? You mean like this?
Yeah. And now that right-hand fraction, that contains all our n.
Yeah.
So if we give a bound on that, say, for example, we notice that the top is positive but smaller than the bottom.
Yeah.
So that thing is going to, or smaller or equal. So that thing is going to be smaller or equal to 1. Then we're doing, then we're actually quite in business.
Right. Smaller than or equal to 1. Okay. Yeah.
So this thing has an upper bound of 1 over I plus 1, for example. In general, it's not very good upper bound, but it works. That's all we care about.
Yeah, okay. Yeah. And then how do we take that back to... that's our relationship between the I plus 1 and the ith element. And are we then going to do, check the first against the last to get a bound for the whole thing?
Yeah, I'm in the meantime, I'm frantically trying to work ahead to see, to get hindsight on what we need. I think we can even do a really gross, dirty estimation. I'm just hoping. I think or we can keep in the back of our heads for now that at least this 1 over I plus 1, if we make sure that I is at least 1,
yeah,
then this will be bounded above by 1/2. Which is a terrible estimation in general, but it will work.
Okay, sure, yeah. But that's just the rate bounded above at 1/2.
So now we have Ti plus 1 over Ti if I is at least 1, we have that this is bounded above by a half. Do we agree with this?
Yeah, I agree with that. That makes sense. I'm just interested to see like how this connects into the bigger picture of the boundedness of the overall sequence.
I'm working out. I'm like frantically trying to work ahead, and I think it will work out very nicely. Yeah. So we have this really gross estimate, like, right? This is like we threw away a lot of information. But it's really simple, just a half, which is like that's a very good win.
Yeah.
So, the next step, what we can do is like remember the point of this was to, like, now we have related 2 successive TIs with each other, but like now I want to do some general ones. Let's say some TK or some TI.
Yeah.
And it's quotient with T1. And the point is that I can write this as like repeated quotients of the intermediate step. Like, for example, T3 over T1 is nothing but T3 over T2 times T2 over T1.
Okay, yeah. And each time we're getting at least 1/2 change.
Exactly. So in each step, and you can do this for some general K to consider what is TK over T1.
Yeah.
That this will be 1 over 2 to the K minus 1. To give this bound above.
It'll be that times whatever the first term is.
So I guess let's write it out and be careful. So we remember that we do have this assumption that our steps work at least for I at least 1.
Yes.
So we should, in our big sum, we have a T0, and then the rest of the terms, like for I bigger or equal to 1, I'm gonna write Ti as Ti over T1 times T1.
Ti. Can you say that again?
So we have some big sum, right? T0 plus T1, blah blah blah, all the way up to Tn.
Yeah.
That's our big sum we're trying to estimate. And I'm saying, well, T0 we will leave alone. Yeah. And then for the I bigger or equal to 1, I'm going to write Ti just as Ti divided by T1 times T1.
Times T1. Right. Yeah.
So I can factor out that T1, and then I have a whole bunch, like some sum of Ti over T1, where we have a bound. And luckily, because I had hindsight and I worked ahead, we made sure that this bound works exactly like we want.
Right, and the bound. Wait, should this be to the n right here? If we have,
there should be a sum, right? We have this. So we have first a T0, but then we have a sum over the Ti from I equals 1 through n.
Yes. Oh, okay. Oh. Of the ratio between the I and the first times the first. Yeah, okay, I believe that.
Exactly. Like that looks really nice because we can factor out the the T1, right? This is the common factor. And then on each Ti over T1, we apply our estimate of like this power of 2.
Right. So the common factor is that, and then we're just going to get a whole lot of 1/2. And those 1/2 will keep multiplying together, and then we would get a k minus 1. We'd get something like...
K is in our case just I. So we will get the sum, we will get the sum from I equals 1 to n of 1 over 2 to the power I minus 1.
Yes. And
exactly, and we still have that T0 at the front, and we still have
right.
this whole sum times T1. Yeah, the T0 in the front we're still missing. Kind of, that's still out there.
I see.
But now in any case we can now we don't have any dependence on the Ti nodes. We just have a T0 and a T1, which these ones we can just explicitly write down if we go back to our definition of what they are.
And choose 1 times 1, which is just 1. And choose 1 times 1 over
exactly.
n.
Like both of them will just be equal to 1, both T0 and T1.
But we still do have a 1/2 in the denominator. But is that...
I mean, now we can fill this in, right? Because what we get is 1 plus the sum from I equals 1 to n of 1 over 2 to the I minus 1.
Yeah.
And now I can give and this works for any n, because this is what we wanted to bound. So our original thing, this 1 plus 1 over n all to the power n, is bounded about by this infinite sum, kind of. Well, not infinite, this finite sum by the n.
Yeah.
But this sum is just like, yeah, we know what its limit is. Yeah. I guess you should really use that here, I hope.
Yeah, that seems reasonable.
It's just a geometric theory. You should have seen that by now.
And the limit is just going to be 1. Well, no, it'll be greater than 1, but we're technically supposed to find...
that the limit will be equal to 2 if you let n go to infinity. So you have 1 plus something where the limit goes to 2, and it's like a strictly increasing thing. So the whole thing on the right is bounded by 1 plus 2, which is 3, which is what we want.
Oh, I got you. Yeah. I was confused for a second because I thought we were adding these three things together, but this is just multiplying. So we are gonna get 3. Just like 1 plus 1 times 1. Oh.
Yeah. I see Pepe in the chat has a probably much better way to get this bound with the 1 over 2 to the power I minus 1. Let's see. Do I immediately believe this? I mean, I believe him, but I don't know where he gets it from. I guess it's inherently, probably it's just literally the same thing we did. We just brought out a lot more steps in between. But yeah. I think it's the same.
Yeah.
But yeah, the key step is to get this bound for this TI business.
Yeah. Wow, that is very clever.
Yeah, you see the whole argument?
Yeah.
Also, it's kind of cursed now. It's just 1 plus 1 times 1 is 3.
Yeah. This is a little nasty, like having to dig into the definition of binomial and then canceling a bunch of factorials. I like fully understand it. I guess it's just there's a little bit of friction there.
Yeah, it's not the most straightforward one. But I guess just coming up with this trick with this TI is kind of a little bit hard, but otherwise I think the idea is kind of reasonable, right? That at this point you might want to use the binomial theorem to expand this out and then to get a bound and some sum. Yeah. And then let's just bound each term of the sum.
Yeah.
And then how you come up with this bound is up to you. Also, what Big Pepe, Big Pepe, what you're saying, I believe you. And I also, the step you're explaining, I'm also completely fine with. It's just, how do you immediately get this step, n choose I divided by n to the power I is strictly less than 1 over I factorial, right? Because that's the interesting step. And that's what we did with this little trick, with one extra step. But if you have some really easy step for that would be interesting. The other part, the 1 over I factorial is less than 1 over 2 to the power I minus 1, that I immediately believe you. That's fine.
Yeah. Soul Matrix just came to hate on math.
Wait, what?
This is the latest chat.
And choose I. Yeah, I don't know. I feel like Pepe is kind of doing the same thing as us. It just brought it out with more in between steps.
Yeah.
Because he also used the bound n minus I is less than n. That's kind of what we did. Okay. Well, I think the last exercise or last part of the exercise is like ridiculously easy, right? It's just conclude that the thing converges.
Yeah, and I mean it's bounded and increasing.
Exactly.
So
Or monotone. There's
yeah.
a crazy screw up in this exercise.
Yeah. That is pretty easy.
Now you can say that you actually know how to define E properly and like you completely understand the proof. Like this is why the number E is well defined.
Yeah, that is a great point. Yeah. I mean, if someone asked me that, I would be able to whip this out. Probably, yeah.
Exactly.
It depends on how long it is from that time I've proved it, but yeah.
That's true. Also, okay. Sure.
I
But
think
is this like were questions from like an actual exam from last year, or was it just like practice questions?
it's unclear. So, I mean, she has that. This is like a list of practice things. Some of them are not even like there's something that talks about the integral test. I don't think we've even covered that. So I'm not sure. Some of these questions seem a little bit dodgy. Oh, I'm not gonna.
Yeah, that's not an exam. That's gotta be crazy. That's like a lot of questions. Sure, you can just whip that up.
She does give this
Yeah,
exam.
you haven't even defined what an integral is, so you certainly cannot use an integral test.
Yeah.
Do you know like how far you'll cover? Like because it's like a whole semester your class, right?
Yeah,
So,
it actually it says so somewhere. Let's see. Probably in the syllabus. Although I don't want to like dox my teacher.
fair enough. I mean, we already know who she is.
Yeah, that is true. This is a public institution.
Yeah. She was the one. She did some really cool things I saw on her homepage, like research wise. Like I mean, she does applied stuff, which is kind of meh, but then she uses things like sheaf theory, which is that's some cool stuff. That's really nice.
Yeah. Oh. Most of chapter 6, and if that permits chapter 7.
Is this from what's it called? Abbott's book?
Yes. Which chapter 7. So up to the Riemann integral. If time permits. So
chapter 7. The Riemann integral. So basically the whole book minus the additional topic. That's nice. Fair enough. It's like I think that's like I would say pretty standard real analysis class.
Yeah. Yeah, it does seem pretty standard. Also, I mean, dude, this math is absolutely like the hardest of the hard sciences. I'm starting to believe. Like, it's
Okay, but
I don't know. It's just like it kind of underpins everything. Like chemistry and biology and stuff are like sort of abstractions on top of math in a way.
I mean, in some way. On the other hand, it is different, right? It is like a deductive science, and all the other ones are inductive. So it's a bit
true.
In some sense, I feel a bit weird to say that math is a science. I like to be quirky and say it's part of the humanities, but people don't agree with.
Yeah. Yeah. I guess I can see that. Yeah, but also like some math models reality more than other does. It
Yeah,
seems
that's
like.
very true. But then, I mean, there's some deep questions. Is that just because we've always done it that way and it turns out nicely? That's really what math is about. Because like when we do a real analysis, we're not thinking about modeling reality. When we apply some fuck ass triangle inequality, when we're
Yeah.
coming up with some crazy crazy shit like this.
Yeah, yeah. I mean, but honestly, also you could argue like the triangle inequality is based in like observable geometric facts, and like even the binomial
True.
distribution is like that's just how stuff is counted.
That's true. It's very much. I mean, yeah, all these abstract things are very much inspired by of course, like real world needs. That's very true.
Yeah.
Yeah.
Most abstract, not necessarily most hard. Yeah. That's fair, I suppose.
Yeah. I don't really like when people say it's like super hard or they complain like math is the hardest thing. I don't know. I feel like this is more of a education system, type thing about how math has been perceived by people from a young age and stuff. I don't believe it's the hardest thing. It's a bit different.
Huh. Yeah. Yeah. That's a good point. I mean,
I
I
mean, yeah,
would
you will,
buy
because you'll
that.
often hear like, oh, hard is your degree or something. Like, how much math is there in the degree? Which I don't think that's very fair nor true. It's yeah, I don't think like math is inherently hard. Which sometimes people look really weird at me when I say that. But I think yeah, it's more so like how have we been taught to engage with math and to think about it. And people, when they like people are not into math, it's like as soon as they hear like, oh, you do math, that's so crazy. I'm not a math person. I could never do that.
Yeah.
Like imagine saying that for like English. Like, what? You are an English major? Damn, I cannot read. Like yeah. It's kind of crazy.
Yeah, I've never made that equivalent, but that's really funny.
It's kind of yeah. Maybe I'm stretching it a bit, but you get the idea, right? It's like yeah,
You're a nutrition major? I don't eat.
exactly.
Yeah.
Yeah, but like I did some like in my undergrad. I did like for fun some courses outside of math, like in linguistics, just because it was fun. And
Yeah.
like it was yeah, it was not necessarily like less hard. It was just different, right? It was yeah, I don't
Yeah.
know how to explain.
I I would say that too, honestly. Like I'm taking linguistics right now, and it's like it's not easy. It's a pretty complicated built out field itself.
Yeah, like what kind of class in linguistics are you taking?
It's just introductory linguistics. It covers like phonology, phonetics, like kind of all the major areas, like a little bit.
Ah, okay, yeah, yeah, that's nice. Yeah, I did like also it was kind of introductory. The one on like which was more like semantic, so it was more towards this math philosophy, what is meaning kind of thing, which just
Right.
kind of
Yeah.
tickled my brain.
Yeah.
So I kind of like that. And they also did like covered like uh, propositional logic and like a bit of basic set theory,
Oh
which I did
wow.
that
Yeah.
did not. So like I was doing this like while I was in the last year of my math thing, and then in the meantime I had some course where we did like very basic set theory. But somehow
Yeah.
I still got the credit. I'm not complaining about
Yeah.
that.
Yeah.
and and then I also did like one course on sociolinguistics, which is like completely different, very much like real social sciences, which is so very different from everything I did up until that point. But I think
Yeah.
it's like in general, like for my education one of the most important courses I did in my undergraduate degree.
Really?
That was pretty. Yeah. Just I mean, yeah, to be like, I don't know how to explain it. Like just how to for like evolving yourself as a person. It was also kind of like in the right place at the right time for me.
Yeah.
But I'm always interested in very much like how does language shape our reality and how we see things, and like we often think about like how do I say it's like language in terms of like, oh, this language is, I don't know, more beautiful or more whatever it is, or we have some very like objective notions that we pair with language, and this whole course was like, yeah, this is kind of all like just made up. It's just how our culture perceives things, and other people do this completely differently. So like, yeah, there is no correct way to speak, in some very strict tense and all these kind of things.
Yeah.
I thought that was really cool.
Yeah. That is, sometimes it's interesting, like a class will be very interesting to you and other times it won't. And it's right place at the right time is important to recognize.
Yeah, that's true. It's kind of hard up ahead. I mean, I guess that's in the American system, the advantage is like kind of forced to do these courses. So I guess at some point you're bound to find a nice one. I guess you also have some shitty ones in between.
Oh, big time, but, yeah.
Yeah. Yeah, for me, it was kind of like lucky in this sense. I was just at the end of my degree. I had like done most of the pure math courses that I was interested in, like all the algebra ones and stuff.
Yeah.
So I was like, yeah, I just need to fill like half a year before I graduate. And I just signed up for random courses in other departments. Yeah. And I kind of stumbled onto this linguistic stuff, which was very cool.
Yeah. That makes sense. Yeah. Do you want to do another math problem or two on this?
Yeah. We can do one or two more.
Okay, cool.
Let's find an interesting one.
All right. Did any of these strike you as interesting? Proving
well, the first one, you can do that by yourself.
Yeah, that's easy.
This the also... second one, I think we did this implicitly last time. I think Big Pepe gave a nice argument.
Yes, we did. Yeah.
So can you tell me, like in words, how would you prove the second one?
It really is just going to come down to like some algebra in the epsilon step. And what is the trick for the algebra?
What's like the big theorem that you want to use in the end to say that it converges? Like, what's the overall strategy you're gonna use? Big Pepe, no spoilers, please.
Shoot. What was the trick for this? Some kind of triangle inequality.
I'm thinking of like a big theorem, which you already mentioned today, and it's like to conclude that a sequence converges, a certain kind of sequence.
Bounded and monotonic, you mean?
Exactly. Right? This as a sequence, this series is gonna, with every term, it's gonna increase because you keep adding positive things. Right. So we just have to show that it's bounded. Strictly increasing is like almost immediate in this case.
Yeah.
So the only thing actually we have to prove here is boundedness.
Right.
So that's kind of the big idea. And then to actually show that it's bounded, indeed, we I don't remember in what context, but I think we like basically did this like a few days ago, where we're gonna estimate each. We're gonna give an upper bound for each term of the sum, and Big Pepper had like a nice trick for this, where we're gonna do this with some quadratic. I think it's like in n squared plus 3, we're gonna estimate by like n squared minus n, something like this. And then you could do partial fraction, and like all the terms would like cancel each other out except the last one.
Right.
And from that
Yeah.
point,
Yeah.
so that's, I think that's the strategy, right? Except I'm not fucking it up.
Yeah.
Yeah. I'm looking again, like, why the fuck is problem 3 fucked up again? Or is this the one we actually...
No
this
problem.
is the one we consider last. Right?
Yeah, it's
With
just
all
like that.
horrible height settings of fucking... It hurts me so much looking at that and that, like, 20 kilometers of white space between the int and the S1. My god.
Yeah, I mean, it is what it is. I guess
Yeah.
it's also just wrong. Like, either this is the inequality is wrong, or she meant closed instead of open.
Yeah, I think, either she has to say closed or she has to do a strict inequality. Yeah. So,
I mean,
3 is a bit, it's just definition.
Yeah, which I feel pretty comfortable with, I think.
How do you feel about 4?
Any finite set is compact. Set of compact if it's closed and bounded. A finite set is bounded, right?
Yeah, that would be a finite set very bounded.
But is a finite set closed?
Well, it better be, but why? So what was our definition of closed?
Contains all its limit points. I mean, there's also the other definition, like if a sequence is in there, then what the sequence converges to is in there. That's
if you have a convergence sequence and every term is in the set, then the limit also better be in the set.
Yes.
Yeah. I'm thinking of there's even another way where it was this characterization of like another way to say compact is every open cover has a finite subcover.
Yeah, that's another way to go about it. Every open cover has a finite subcover.
This will actually, and that will make this problem quite easy actually.
Because it's a finite
So I think
set, you could say, you could just like take split it into a bunch of pieces, and call that the finite subcover.
I mean, the point is you're given an arbitrary cover. You don't know what it looks like, and you have to exist. Show that you can. So it's like some collection of opens, and the only thing you're given is like this collection may be infinite, but you know that it covers the whole set. So every part of your set, every element is contained in at least one of these elements of the cover. Yeah. And then you have to say like, can I choose only finitely many of these? Such that it's still covered.
Yeah. Okay.
So, how would you go about this in this case?
And we're starting with the fact that the set is finite.
Mm-hmm.
Well, I mean, could you choose? If it's finite, there's like only, let's say, n elements, for instance. Could you choose like sets using that n as like an index somehow.
Yeah, I guess. Don't really have to, but I guess you can phrase it that way. So another way, the thing is like you have finitely many elements.
Yeah.
So you have some cover, and you pick some point in my set. Then I know that there exists some open in this cover, which contains my element. Just by the fact that it covers, right?
Yeah.
So if I choose for every point in my set, I simply choose such an open. So let's say I have 3 points, and for the first one I pick an open, for the second one I pick an open, and for the third one I pick an open. Kind of by construction, if I just consider those, well, 3 in this case, those 3 opens, I kind of constructed it that every point of my original set is still in there.
Yeah.
So yeah, this subcover is it's still a cover, and it's finite because I only had made finite many choices. Like I started with a finite set.
Yeah, I see. And
so yeah, so now from an arbitrary cover, we've made a finite subcover. So this is kind of like I think it's a neat little argument.
Yeah, and you're picking 3 just specifically, but it could be any number of finite.
So in general, if you have n points, then you for every point you pick an open, and as long as your set is finite, which is our assumption, then you have picked finitely many opens, so you have a finite subcover.
Yeah, gotcha.
And this is like a neat proof. Note that we have used absolutely zero about where this is happening in the real numbers or anything like that. What we've kind of proven here, because like this, every cover having a finite subcover, like this is the definition of compact you will see in topology. Like this is the morally correct definition of compact. So
yeah.
So this, what we've kind of proven is that in any topological space, any finite set is compact, which is something much more general. And that's why this proof works so general. Like there's nothing specific about the real numbers.
Gotcha. Yeah. It's kind of interesting, this class like has you learning topology slightly at the same time.
Yeah, I think they do that quite nicely, that you learn about these. I mean, that's also I'm thinking back to how we did it. We talked about metric spaces and opens and closed. I don't think we talked that much about compact. But I guess this is kind of like the precursor, right? This is what should motivate topology, because in topology, or like here in analysis, you see like a lot of these things talking about like these geometric things. I can do this only in terms of like open, closed, right? Yeah. Like it's all fun and nice that I have this metric, but a lot of these properties I can express just in terms of open and closed, and that's kind of where topology comes in. Like, what if we forgot that we had a metric? What if we only had like these abstract open and closed sets? And like, how far can we go from that?
Right. Yeah.
But I think it's also this book, the Abbott's book, is quite nice.
Yeah, a lot of people seem to like that book.
Yeah. Because originally you had some like apostle or some like one of these old bricks, right? Did your teacher just give up on that?
No, I mean, I was just like, I didn't read the syllabus carefully enough. Like, the apostle she uses a lot of the proofs in apostle. So it's like a 2 textbook course. But
I see, that can be annoying.
Yeah, I definitely prefer this understanding analysis. Pepe says you can prove sequential compactness directly. If AI is a sequence
Uh,
by pigeonhole, some number appears infinitely many times that gives us a convergent subsequence.
yeah, yeah, that also works. So this was this idea of compactness that we do, like any sequence has to have some convergent subsequence, and this limit has to lie inside the set itself.
Yeah.
So it's indeed, you have like, let's say, finitely many points. And if you have some sequence within these finitely many points, right, no matter how you define this sequence, one of those points has to appear infinitely many often in the sequence.
If it's convergent,
And
you
this
mean?
defines you like a, not just for the fact that because it's a sequence and it can only take finitely many values, but like the sequence goes on forever.
Ah, yeah, I see. Yeah.
Like you can't evade all the points all the time. Like you have to have some point which appears infinitely often, and kind of that defines you a subsequence which is just constant after a while.
Yes.
And well, that thing is, yeah, so that's convergent, and the limit is inside your original set. So it's compact.
Yeah.
Yeah,
That's quite clever. I mean,
yeah, or then in the other way, what do we say? Bounded plus closed. Bounded, we already said, is true. Why is it closed? Or closed is if, I mean, closed is also a very similar argument, right? Where you think about it as you have some sequence inside your finite set,
yeah.
and you're given that it converges, and you just have to show that it converges to something inside a set. It's kind of, well, what does it mean if you have a sequence just inside this finite set and it converges? I think it's not too hard to see that your sequence must eventually be constant. Can you believe that?
I can believe that, yeah. Because you're going to run out of terms to go to. There's only finite number.
Exactly. Like, because it converges, it has to get arbitrarily close at some point. But between any two, because you have only finite many points.
Yeah.
At some point, the distance will be just too small that it can't jump anymore.
Right.
So at some point, if your epsilon, you make it small enough, you have to stay within one point.
Yeah.
So eventually it has to be constant. And then, then it just converges to that thing it's constant at. I mean, yeah, that's just what it is.
Yeah. And
so there's a lot of ways this is compact.
I guess I find that approach slightly easier than the finite subcover approach, but I guess I just have less exposure to topology.
Yeah, no, that makes perfect sense. I just want to say it like that this subcover approach gives you something like very general, that this actually, because like in these other approaches which are just as valid, but it kind of is like, it feels like we're somehow using the properties of like the real numbers and what's going on, but like the point is that actually nothing special about the real numbers here.
Gotcha. Yeah, I see.
Do you want to try the fifth one?
Yeah, that's just a...
Yeah. Also, I'm looking at these 5 problems. These ones are so much easier than whatever those previous lists was. Like, this crazy difference.
This list, you mean? Yeah.
Yeah, like, how many problems are you? Anyways. So yeah, like 1 through 4 is 1 through 4 I think you're happy with, right? I guess for 2 it takes out some, it would need to write something. But I think in principle you can do it. So 5 is like the only one.
Yes.
Or do you want to do something from the hard list? And that's also fine by me. And try it.
I guess let's just do 5. I seriously doubt anything from the hard list is actually going to be like. I mean, that famous last words, and like I have my exams on Thursday, so I'm likely going to stream tomorrow and Wednesday.
Okay, nice. I have to see. Maybe I can catch it. Depends on the time. But I'll see you
cool.
how you are when you're released for the exam.
Yeah. Flow function.
Yeah, we can pick one. Okay, yeah. We know what continuity is. This sounds like a standard exam question, to be honest.
Yeah. Is continuous in its domain. Yeah, and this is just going to use the Epsilon-delta definition.
Yeah, I think here they just want you to go good old Epsilon-delta.
Yeah.
So let's think about it. What do we actually have to prove? We're having to show that the function is continuous on some domain. So let's try to think. What does this actually mean? What are we being asked here?
Yeah, we have a very restricted domain too. It's like we're going to show continuity for C where C is between those 2 points, like an arbitrary C, and that boundedness of C might be useful in algebra at some point.
That might be quite nice. That's already a good observation, and indeed. So like the first level of unpacking what we want to show, we want to pick some arbitrary C in that interval.
Yeah.
And show that the function is continuous there. And so what we want to show is that the limit of f of x as x goes to c is just the square root of c.
Yes. We want to show also, there's something with the definition. I usually like confuse it, but it's like x minus c implies root x minus root c. Just want to write out the definition, so.
Yeah, I think today the stream is like extra behind. It takes a while.
Huh? Yeah, maybe I have the settings on something weird.
But yeah, looks good what you have.
So we're looking for a delta in terms of epsilon.
Exactly.
Or an epsilon in terms of delta. It's a little bit.
Always epsilon in terms of delta. Sorry, delta. Oh, I'm delta. My bad. Almost stumbled there. Yeah, with these always you have to like think of the order of the quantifiers, right? It's like a for all epsilon, there exists delta. So you first choose an epsilon, and then you have to show that a delta exists. So you may choose your delta in terms of epsilon because it's like a delta is only quantified over later.
Okay, yeah. And the order of this like implication that I have set up is like you could do it the other way too, theoretically. Like you could do.
Mm, what do you mean? Like the implication, you can't just flip around. I don't know if that's what you
No, I guess not. But thinking about like this is like uh, two input values, or like this is kind of before the function is applied. Like the values before the function is applied implies that the values after the function is applied is less than some epsilon. But could you do it the other way around somehow? Like the values of this is just like
I
purely
mean, I
from.
guess could take a contrapositive. It will not be
Yeah.
that flip it. It will not be that nice.
Yeah, not not that
Uh,
that's useful. I'm just wondering if like you could define this in terms of like y values implying x values rather than x values implying y values.
I mean, if your function is not bijective or injective in general, not really, right? Because there's like multiple x values could correspond to the same y value, right? If your function is
Ah,
non-injective.
yeah. Yeah. But if it was bijective, you could freely use if and only if.
Um, mm, not no no, still no. Because like there is a one-to-one correspondence, but like your function could still shrink the distances or blow them up in a really weird way if it's not continuous.
Right.
So
Yeah.
uh, yeah, I think that's truly still something different logically.
Yeah. Okay. So our delta.
So I think like we always want to work backwards, right? We want this epsilon. Like, can we express our square root of x minus square root of c in terms of this delta thing, so that we can get an expression of delta in terms of epsilon.
Hmm. I mean, is this like the same thing as, because this is just x to some exponent minus c to some exponent. Is this going to use
Yeah.
like uh there's some way to cleverly factor this using.
Yeah. I mean, we don't directly. I mean, yeah, we want to do. There's some factor idea going on. That's very much. Um, but we don't want to factor the thing that we have right here necessarily. I think what we want to note is that we can rather factor x minus c using different squares.
You mean that, or do you mean like factoring x squared or square root x minus square root c using difference of squares?
Neither entirely. I mean, you have x minus c,
Yeah.
and if you just know that because everything is positive, we don't really have to worry about the signs of the square root. If you know that x is just the square root of x squared and c is just the square root of c squared,
Yeah.
then that's a bold first chat message. Damn, you're cooking.
Um. Wait, you. square root. But you're not talking about
I'm
just.
saying,
Yeah, go ahead.
what were we? Okay, I'm talking about something really straightforward. Nothing deep going on.
Square root x.
Yeah, exactly. Like this gives you your x minus c, right?
Yeah, it
So
does.
in terms with this factorization, we can write square root of x minus square root of c simply as x minus c over square root of x plus square root of c.
You can over. You can combine like that?
Wait, let's see what pops up. So we don't need this square root on the outside of the x minus c. I'm just saying x minus c, and that's just that over the square root of x plus the square root of c.
Square root of x plus the square root of c. I guess I'm not seeing how the algebra gets from that step.
As in, like we have a factorization. We have a product. We have x minus c is a product. It's the square root of x minus square root of c times square root of x plus square root of c.
Yeah.
Right? That one you see. And then I just both sides I divide by square root of x plus square root of c. So it will cancel out on one side.
Square root of x.
That's all.
Yeah, that is clever though. Oops.
And here I think it will indeed be quite useful in a minute that we're only on this like bounded domain.
Yeah.
Because now this x minus c we can bound in terms of delta, right?
Yeah.
So if we make sure
but what will the we don't want a c in there, but it's okay to have an x in there?
no other way around. The c is fine because we're doing this at every point in c. So c is like a fixed constant for us.
Yeah,
c
but
is fine. We don't want to depend on x anymore.
How do we get rid of that x though?
Exactly. So this x minus c, that's delta. So we now have delta over square root of c plus square root of x.
Delta over square root of c? Oh, yeah.
Yeah, square root of c plus square root of x in the denominator.
I see.
So you can think of so now you want to, I would say, consider that the interval we're on to make like a really easy estimate, to get even totally like rid of that denominator.
Well, we've got, but that only gets rid of the c component of the denominator, right?
All right, let me see. What are you gonna do?
Like the c component of the denominator is gonna be greater than 0, less than equal to 1.
But remember that our x is also um, our x also lives on this interval, right? That's kind of like
Oh, right.
down careful.
Yeah.
But x is only within the domain of the function.
Right. I forgot about that. Yeah. So these are less than or equal to 2 in total.
Yeah, but we have to be careful, as in, like it's in a denominator. So we kind of want the
We want the others
upper bound
bound.
for 1/. So we want a lower bound for square root of c plus square root of x.
Which will approach 0. I mean, we want
And
a
you just, in the
lower.
end, if there's a c in there, it's fine. We just want to get rid of the dependence on the x.
Oh, x plus 0. I mean, or square root c.
That sounds right.
It's, well, 0 isn't included, so I mean,
Yeah, so square root of x is also. So you just get delta over square root of c. Exactly. So you want that is less than your epsilon. So that tells you how to choose delta in terms of epsilon.
tells you how to right, and then we have to work backwards.
Exactly. Or I guess, yeah. Or I guess the way we have it, I don't know. Somehow you always manage to do it that in the end you kind of have to go frontwards. Like you've already kind of written it down the way you would expect it in a proof.
Yeah.
A little bit at least. I mean there is some funkiness going on, but
Yeah, I don't know how to line split this better, but yeah, okay. And so we just pick our epsilon to be delta.
our
delta over square root c.
We pick our other way. We pick our delta to be epsilon times the square root of c.
Gotcha. Yeah. Because
then if you go through the math, given that absolute value of x, and like of course you kind of also should worry about the absolute values.
Yeah.
But it will work out. It's not that big a deal here. But you'll get that. So you consider like absolute value c, or sorry, absolute value x minus absolute value c, that you write as this quotient as absolute value x minus c over absolute value x plus absolute square root of x plus square root of c on absolute values, and there you do your bound, and then you will see that it's less than delta over square root of c, and then you know that that's just epsilon, and then you have what you want.
Yes. Yeah, you're right. I did kind of write it forwards in a way.
Yeah, I don't. You managed to do this. Also, we know. I guess if you want to do it like really precise in a proof, I guess you should note that our step here makes sense. Like that, I wrote this quotient, or we did this estimate thing, because like 0 is not included in a domain, so we're guaranteed that we're allowed to divide by square root of c.
Right. Yeah. That, I guess that is important to say.
Yeah.
Yeah. Wait, this step transforming.
Can you maybe open it in the that it's compiled, because now it's a bit hard to read.
Yes. Oh, that's very janky looking. My syntax highlighting is kind of messed up, I guess. I mean, that's kind of just scratch work. So starting with x minus c less than delta.
Yeah, so we're given that absolute value of x minus c is less than delta. This is our assumption.
Yeah.
And then we consider the thing, we consider absolute value of square root of x minus square root of c, and we do our estimates and stuff, and then we should in the end get that that's epsilon that we're done.
Less than. Let's see, less than square root c epsilon. And then x minus c. Well, I was forgetting the absolute values in the scratch work. Oh well.
So yeah, in the end, you should end up with just epsilon on the right, not square root of c times.
So I have to move this.
I guess the structure, the outline of the proof.
If I do this though,
I mean, just in the end, yeah, you just get less than epsilon is what you want, right?
yeah. Oh, but I don't have.
So something is going. I think you're making it like the way you had written it down before is kind of what you want. Like you want to start with absolute value of square root of x minus square root of c, and then you just rewrite that and keep going until at the end of your chain you reach epsilon, and then you're done. Also, good night, Pepe.
See ya, Pepe, yeah. Yeah, this step. Slightly confusing.
Maybe, or if you want, and maybe it will help you to see like one time like a proof like this fully written out. If you want, I could go in tips and you could just see like in excruciating detail like what could where.
Sure, yeah.
I don't know. Yeah, if you want, you can make like a public tip, and I can do that quickly.
Oh yeah. I think we still have the same.
Because I think it helps to see it like written out in like all the detail.
Yes. How do I access chat? Discord is so confusing. I'll just drop it in.
Yeah, if you can drop it in the YouTube chat, that's great. Thank you. Please sign in to access this page. Hell no. Why do I have to? Before I never had to make an account. Okay, it wants me to make an account. I guess I can do that. Give me 1 second. I'll just use my junk email. They won't know.
Epsilon-delta arguments, the game starts by being given an epsilon greater than 0, and then having to find a delta that depends on the given epsilon.
It says the project is not found, ever. Damn.
Really? Oh.
Yeah, I don't know.
I might have copied the wrong... I just copied the URL, but it might be better to generate something. I dropped a new link.
Might have just made the account for nothing. No, it's fine. Oh yeah, it's working now.
Yeah. Okay.
Yeah. Okay, so I'm just gonna start writing here. Oh, and then I have to on the floor, on the go, make up like tip notation. So we're gonna like carefully introduce everything. So let's see. So first we're given a C. Then we're given an epsilon greater than 0. This one's going to be very pretty, but it's hopefully going to be clear. We're going to choose our delta to be square root of C times epsilon. And now we're gonna prove an implication, right? We're gonna prove if absolute value x minus c is less than delta.
Yeah.
Then something. So I'm gonna, like, to properly set up the implication, I'm gonna assume we have an element, namely x, in the domain of the function. So this is again an assumption on x, both x and m. And an extra assumption was that how do you write not equal?
Equal.not. I have an alias set up. Although you can just write it like that. Actually, I can.
Equal does not work.
I can paste in my aliases.
Nice. Yeah, it's nice to get like this slowly as you do more courses to make like this longer and longer list, and it keeps growing of all your things.
Yeah.
At the end we have some crazy preamble. I have the same thing with Latin.
Yeah.
And so now I have kind of like the setup. Like I introduced all my variables and everything that so we want to show. So we see that so what do we want? Square root of x minus square root of c. Wait, is this not how you do like math mode with like the double of compiling?
No, it's just singles, but yeah, like a space between content makes it multi-line, yeah.
So now I'm just gonna have this expression, and I'm gonna rewrite it just like with a bunch of equality. So this is x minus c over square root x.
I think you might need parentheses around the.
Oh damn! Yeah, I see that. That makes sense. That makes sense.
Although they should let you not do that because the absolute value is kind of like parentheses.
Yeah, that's kind of cursed. I mean, it's because you don't really have like how do you say curly brackets like in text where you can like say what goes where. But
Yeah.
it's fine. But I'm curious. Can I do something like this, like in that, and it's like what auto size it? No, unfortunately.
I think there might just have another name. It might be paren.
Yeah, probably
Dot left.
something similar.
Like that, maybe. I don't know. Oops. Okay.
Oh no. Oh, that's not something like this. Okay, that's better. I keep having so much this instinct to write like a backslash. It's truly such muscle memory. It's crazy. Square root of c.
Yeah.
Yeah. So I mean, this is. I mean, it's already it, but it's kind of like it's all there. Like if I were to hand this in, there would be more text in between. Like if I'm being really like how to write it like a proper math book, like saying like what I used in which step. Like in this step we use the assumption that absolute value of x minus c is less than delta, and in this step we did that.
Right.
But I think this already makes it very just clear, right? We've introduced like like let c be that, let epsilon be that. We choose delta this, and we chose x to be such and such an arbitrary.
Yeah.
I think it's, like writing it down like this can kind of be cumbersome, but it's like it helps a lot with the structure of the argument. Like what is chosen before what, and what are the assumptions on everything.
Right.
So this shows the limit x to c. Not how you do it. Oh yeah, right. It's just like this. X to c. Square root of x equals square root of c. Therefore, square root of x is continuous. But it's always hard work.
Yeah, it is a hard word, yeah.
Right? I would say that's a pretty complete proof.
Yeah.
It's very.
Yeah, the algebra is actually pretty simple. The way you have it is just a few steps.
That's also like, yeah, if you have like this really understand in your head like what's the algebra and like what should be my beginning step. So like I started with this expression absolute value square root of x minus square root of c. That's what I want to start, and this is something I want to show about. So it's very clear in my head. Like that's the thing that's with a bunch of inequalities. In the end, I want to get epsilon.
Yes.
So like in my head, this is kind of like already how to prove. Like I know that whatever it should be, I should start with just that expression, and I should end with just an epsilon.
Yeah.
And this kind of forces the steps in between to already like be a certain way and like help the structure of the argument.
Yeah, that does make sense. Yeah.
Because otherwise you kind of run the risk of like these what's the nice way to saying like getting all these like equalities, like when you say them aloud, they make sense, or like these operations. But then when you write it down, you get put like implications between things which are not really implied by each other, or equalities between things which are not really the same. And
Yeah. Yeah.
like the flow of how you said it is like a different, it's like it happens very easily.
Right. Yeah. Yeah. All right, sweet. I think I'm gonna switch to finishing some other homework I have for a couple other classes and call this stream here. I'll probably be back tomorrow on it, just to study from the hard sheet.
Yeah, maybe I'll be there. I have to see. Well, good luck with your other homework. For me,